Very good. Okay, well, hello everyone. Welcome to a little Saturday afternoon computational exploration, and we are going to look at lambdas, which is something I've been kind of meaning to look at for, I don't know, 40 years maybe, and somewhat related to combinators, somewhat related to lots of other kinds of symbolic systems I've studied, but this is old Alonzo Church's classic 1935 lambda idea, and I wanted to see whether we could kind of explore the ruleology of lambdas. So Nick has a Packlet that he's put together, so let's start off by getting that loaded. And maybe I'll make this a little bit larger. Okay. And Nick, you're going to tell me a bit about how to use this.
Yep.
Oh, I'm already at line 299 of this Wolfram language session because I've been doing all kinds of other things in it. Maybe I should have restarted it, but it'll probably be okay. All right. So let me see if I can understand a lambda here. So this is an example where the 1, 2 are De Bruijn indices, right?
Right.
So they have been, can I write this out in some form as a function, as a standard Wolfram language nested function or not?
You can write, yeah, there's a lambda function that turns lambda terms into functions.
So it's called lambda?
Just lambda function.
Oh, okay.
Yeah. But I think it's gonna like introduce some symbols for variables that are pretty ugly.
That's pretty ugly. But we notice one thing here, which is that our 1 here, let's see, what are we seeing here? We're seeing our 1 here is not the same as our 1 here, right? And the whole idea, so what would happen if we wanted to have if we had a variable in here that is, let's see.
Actually, do comma alphabet. I forgot about this feature.
Like this?
I think so. Maybe. Actually, let me remind myself how it works. Oh, before, yeah, it's not the lambda function argument. It's you should tag the lambda. There's a function called tag lambda. You can just do tag lambda first with this alphabet. In a string.
I was thinking it was just going to be letter number where it just used the De Bruijn indices. Okay, all right.
And you can even do traditional form. Then it's gonna be even nicer. Maybe.
That doesn't help me very much. Okay. Let's just look at this. So, by the way, I mean, do we think that if we apply this to things, so like this, that original function there, here, this function here, we can apply that function to x, right?
Yes.
Okay, let me make sure that I understand what it did there. So that binds a to x. I don't understand.
Well, let's parse it out. So essentially, this function b applies whatever function it takes as an argument to this x, right? So, and what is it? It's kind of doing more than that.
Let's just do this, just to the sake of seeing what's going on. That doesn't help me at all.
That's why there's some multi-way systems we can try to build.
Okay.
And like function called beta reductions that can just show what actually is going on. Maybe that would help.
So let's go ahead and do some of that. So you're saying, I mean, okay, just so I understand just the scope of this, that's just taking some syntactic form there and being able to parse it like that.
Yep.
Okay. Oh, that's interesting. Lambda converts to a combinator. So we can convert this lambda to a combinator. Somewhat complicated combinator. I mean, is that typical that little lambdas turn into much bigger combinators?
Yeah. Well, it also depends which combinators you use. I think I had an option that also, in addition to S and K, tries to do CB, something else, and I. So it might looks
Can
much.
you enumerate lambdas? Do you have a thing that enumerates the simplest lambda?
Yeah. Yes. Enumerate lambdas.
Right. So Victor is pointing out, and it wasn't to say it, but you're pointing out that automated translation will not give you the minimal form, which is surely true. And now okay, so we say enumerate lambdas. What do we do? Like 3 or something? That's,
Yeah.
oh gosh, that's okay. And so we could say something like, so those lambdas, if we look at, let's say leaf count, is that the right way to assess their size?
I think so. It's a good one. Or maybe just depth, something like that. Because that 3 is essentially the depth of that expression. And the second argument would be the length of application, how many applications is the maximum.
Can I draw one of these? So let's just pick one. Pick a random one. Now, is there a good way to draw this?
You can do lambda smiles. That's like this colorful thing.
Oh boy. I do not have intuition for what these things mean. Can I draw the tree? I just do tree.
Maybe you can do expression tree if it helps. Oh, the lambda convert tree, I think, also makes a better one by default.
Wait a minute, what does that mean? What are these A's and things? What are those doing?
Well, those are, if you tag it with alphabet, they're essentially just arguments. So we show them explicitly.
But what is this?
This is an application.
That's an application. So that's saying this is the head, it's applied to this.
Yeah.
And okay. Okay. So, well, I mean, I'm just curious in terms of, well, okay, another question. These are not necessarily minimal, right? These lambdas, some of these lambdas could be equivalent to other lambdas, right?
Yeah, I guess perhaps. Yeah. By that you mean they can be reduced to the same normal form. Okay.
Victor is saying, can lambda convert turn this into an interaction combinator, which is Victor's favorite representation. What's the answer, Nick? Do you have a thing?
No, not yet. Not yet.
Okay. So that's we need Victor's help.
I'd love to help with that.
Is it something you can do in real time, or is it something it's probably going to be a little complicated? Let's table that for a little bit. We'll come back to that.
There's also built-in arrow form which I was playing with Nick previously, where it's just the default way to do it in Wolfram language. Nick, do you remember how to convert that into your?
Yeah, that's just a traditional form of functions in the Wolfram language. You can also try to turn them back into Lambda expressions. There's a function called function Lambda that goes back in another direction.
Okay. But there's not, I mean, other than renaming the variables, the symbolic structure of one of our functions is the same as the symbolic structure of these Lambda expressions. Is that correct?
Yeah. Well, I guess our functions are also multi-argument functions. That's the only difference.
Right. So there are function things that cannot be, except with currying, cannot be turned directly into lambdas, correct?
Yeah. Technically, you can also introduce like sequences as arguments, but yeah.
Okay. Okay. But let's okay. So what we wanted to do was to start off looking. Let me just get a few. Okay. So I'm asking this question about the equivalence of different terms here. And what do we know about that? Do we know? Okay, so let's just say, let's have a more modest number of these. Oh, that's very boring. What does this do? What does this mean? When I put a 2 in there, is that 2 variables?
It's a depth of lambdas. So how many nested lambdas there are.
Okay.
You can also try second argument. It also, by default, it's 2. That's how many applications maximum are there in the expression.
Okay, so if I say 1, 1, get that. Let's say I say 1, 3. Okay, so let me just draw these trees, just so I might have some hope of understanding what the heck's going on. So
you can try to understand this diagram that I come up with in order to draw those expressions.
Yeah.
Weird. It's just called lambda diagram. You can draw them as little lines with dots. So I don't know whether it helps, but
Maybe you can explain it.
So essentially, it's like the horizontal lines are the lambdas themselves, right? And the vertical lines are the arguments, and essentially the most bottom line is the application. So it really helps to just try to understand it by example. So just
I want to see what happens when I compose these things. So if I have this thing here, it's a lambda. If I were to say lambda of 1 of lambda of 1, what would it look like?
Well, just try.
Okay, I don't understand that at all.
So the 2 dots there, those are 2 lambdas that you have. And because you apply one to another, there's horizontal line at the bottom that it's applied to one another.
Why are there 3 dots? I mean, I thought it would be a 1 dot per lambda.
It's more like 1 dot for also for application too. So
that you make it a different color, maybe.
Otherwise, you wouldn't distinguish some of the terms without those dots.
I don't understand why. Okay. What's a version? So if I were to do this, okay, so let's just do this. Let's just say, let's see, if we want to say nest list, and then we want to say apply, let's just get one of these, lambda of 1. Apply this thing to this thing 5 times, for example. Okay, now let's do your lambda diagram.
Oh, that's cool.
What does it mean, though?
So each vertical line is an argument.
Nick,
Yeah.
what does this mean?
Well, you kind of can guess, right? It's just by the structure of it. It really needs some practice. I haven't stared too much at it myself, but yeah.
Well, and what do we think in terms of equivalences? If we've got two equivalent lambda terms, do we think there's graph rewriting that can be done on these things?
Well, you can certainly do some better reductions in terms of these diagrams too.
Okay.
Hmm.
Well, let me understand the beta reduction story here. So first of all, of these terms here, can there be any reductions done?
Well, try it. There's a better reductions with you just apply it to a term and it will return all possible ones that you can do. So there's none in the first, then there's like 2 for the second, 3 to the
Okay,
Those
so
linear.
let's now just do those diagrams look identical.
Those are the reductions.
No, I know those
Wait,
are the reductions,
yeah.
but those reductions always give the same result.
Not necessarily. In this case, they are the same.
Okay.
Hmm.
But in general, okay. So, all right, I want to see these in terms of trees. Maybe it's not useful, but how do I get the minimal tree out of these?
The minimal, you mean like after you reduce it or something?
No,
Keep-
I mean just without too many labels and things. Is
Uh,
that your lambda?
Or you can,
That your lambda convert to tree?
yeah, and you do some options if you want to remove the labels.
So let's do lambda convert to a tree. And let's just at least do that on this thing here, on this nest. Okay, that's a little bit easier for me to understand. So these are a bunch of lambda of ones, but they're all getting different symbol names here because we're trying to avoid the ones which are De Bruyne identical, but not identical when we write them out as symbols. And then we're just nesting down here. Okay, I get that picture. That picture is a little easier to understand. Okay. Can we look at okay. And so beta reduction on these things does nothing, basically. Is that true?
Oh, you see above that does something.
What does it
Right.
do? They're all identical.
Well, you can apply it again. And again, I think they just will reduce the identity at the end. Right?
Try it. Let's try this. Okay, so let's say we take one of these terms. Let's pick on this guy here. And let's do fixed point list of beta reductions. Oops, very different thing. And I'm going to use, let's just do this. Let's just do first to beta reductions.
Mm-hmm.
What the heck? It reduces.
Yeah, it kind of works differently. It returns an empty list if there's none. So you have to walk around that.
You can also beta reduce one step at a time, right, Nick? You can just do a beta reduce.
Beta reduce comma 1 would do a single one.
That might be easier to understand what each beta reduction does step by step.
Okay.
But you can also try it as a nest while list instead of fixed point. And your condition would be to check for the length.
this should be first. And what should I check for?
Length greater than 0.
No, but that's for this. This is what I care about, being the length greater than 0.
Oh, you mean when to stop the nesting? Something.
No, there's a different function. I think it's called just beta reduce. Is that
No,
different to beta reductions?
I chopped off the. Something went wrong here. Okay, let me just understand in the most basic case what a beta reduction does. So let's take this guy here. Okay, just tell me, what is this basically doing?
Well, it looks for applications, lambda applied to something, right? That's the pattern that it's looking for. And when
Yes.
it finds one, it tries to reduce it, right? And it can be when nested inside some lambda expression very deeply, and it can reduce that.
Let me just understand. If I say lambda function, what's the alphabetic version? Lambda function of what? Lambda tagging, what was it called? Tag lambdas.
Tag lambda, yeah.
Okay, now what does the beta reduction do to this?
Oh, just turned it into identity. This lambda term is just identity applied to identity.
How do we represent that result? How do we represent identity?
That's how you're looking at it. Identity, a function that takes an argument and returns it.
No, I understand that. I understand that. But I'm saying, if I now do beta reductions of this, oh, actually, it's just returning
Results. Yeah.
That's very uninteresting. So, I mean, if I were to nest another level here, another level of lambda, I am very confused.
Well, lambda
Why is
function
this saying, what's that?
lambda function turns it into a function, and your function evaluates to the normal form, right? It goes through
Oh, there's an evaluation going on here.
yeah, the normal evaluation.
Okay. Now I'm not so confused. Okay. All right. I see. So, all right. So, but then, okay, what other reductions are we able to do here? Are there other reductions that keep?
Oh, there are eta reduction. That's another one that's
Whoops, do you have
actually
that?
applies there. Eta reduction. Well, there's just eta reduce thing, and it just basically resolves all the identities. It's a very simple one.
You know how.
Eta reduce. There's just one function, but it's really simple. It's in this case it should act similarly to, or maybe it's doing something different.
I don't remember what eta reduction is. What is eta reduction?
Victor, do you want to pop in there?
Yeah, sure. So when you have a function applied to, let me try to write it. So for example, if you have lambda x and it returns something applied to x, it's the something as that. Let me write, that would be simpler. So like if you have something like that, lambda x, that returns a applied to x, that's the same thing as just a, because that lambda is redundant. It's not actually a computation rule. It's not very useful nor relevant, and you don't also have like an interaction at combinator equivalent to that in the lambda calculus sense. So I don't think it's very relevant here. The main computation rule of the lambda calculus is the beta reduction, and with it you can do anything.
Yeah, eta is sometimes called eta optimization, if I'm not mistaken. Yeah, it's
It's
not actually
more,
reduction.
sorry, it's more like a display thing.
Yeah, yeah, I
That's
get
not
it.
really.
I get it.
It's useful for equality, but like not quite relevant here, I think.
Right. Yeah, right. I mean, it's getting rid of the unnecessary kind of, you don't need to describe it with an additional variable. It's getting rid of that unnecessary variable.
Yeah.
Okay. So now what we had started doing, we're just going to do an exploration of possible. So I'm still not really, I mean, do you believe in this representation, Nick? Should we really try to understand it?
Well, I based on it on one of the known representations, but it's just highly improved.
Okay, well let's all right. So then I'm gonna just take a look at this. Okay, so we've got lambda diagram. It always helps me to see lots of real cases here. Actually,
You can like I posted a link into chat. It's like how what those diagrams was inspired, which diagrams, and it's much more complicated.
okay, it's John Trump's version of this, which it seems very clever, but I've never understood.
Yeah, I just realized that you don't have to actually nest this height of this diagram. You can just stack everything on one single line. So and just put some dots there.
All right, well, let's see if we can't understand. I'm just going to make one attempt to understand these diagrams, and then if we can't, we give up and we okay, so let me just make them smaller. You don't have, does it take image size options and things?
Yes, I think so. Maybe not. I'm actually, yeah, should.
There's something to do at the bottom left is kind of the application, Nick, and then everything kind of compresses down bottom to bottom left every time you do reduction.
Well, any application is just on the bottom line. In the Tromps notation, it's usually just on a different level, but here we're just putting it on a single line and just separating them with dots.
What does composition look like in terms of these diagrams?
Composition, well, composition is just application there. What do you mean by composition?
Okay, so what is it? What do you do? If I have one of these diagrams, I want to apply it to another diagram, what happens?
Well, you can see that they're just going to be just concatenated horizontally, somewhat. You can test it.
Okay, let's test it. Okay, so let's say random sample. Oops. All right. Enumerate lambdas of 2. Okay, so we've got 2 random lambdas, and we've got lambda diagrams of each of those. Okay, now we're going to take, isn't there a function, is it construct? What's the function that will give me this applied to this?
Well, either construct or apply. Yeah, well, depends how you use it.
I'm just forgetting how construct, doesn't construct take a list? Oh no, it doesn't.
Oh, just two lambdas there.
Yeah, okay.
Without lists.
Well, let's just take.
You can literally just put an @ symbol between them.
Well, I know. So it's this. And then we say lambda diagram.
Right.
All right, that is somewhat useful to me. Is that the general way that things compose? That you're just putting
I think so. Yeah. Yes.
Okay. So what's the other operation other than composition that puts these things together? So I mean,
Well,
You're
There's nothing.
saying in terms of diagrams, yeah, I see. So here, the composition is just adding these things, basically.
Yep.
I don't understand what those dots at the bottom are.
Well, think of it as this apply symbol, right? So it also looks like a dot application in the language.
Okay. Now, if I look at the tree version of this, oops. Let me just get that lambda. I don't have to worry about De Bruyne renumbering. And I could De Bruyne renumber this, and I might get smaller numbers here, right? But if I just do the application, I'm never going to get confused. Is that a true statement?
Sorry,
The
what do
De
you
Bruyne
mean?
numbers I might be able to optimize the De Bruyne numbers, but they'll never tangle themselves up with something applied to something. Is that true?
You're asking if
Okay.
you just apply something to something else, and no, I mean you can have naming capture, so that's you need to kind of sanitize the term when you do a beta reduction to make sure you shift some Bergin indices in a way that does not clash, and then you have like two different variables with the same name. That's one of the problems with this representation. I don't like this like kind of Bergin representation. I don't think it's very pedagogical, and it's also not very efficient. So usually I tend to avoid it. I think it's very confusing to just use.
So what is your alternative?
I really like the textual notation. For example, you have the lambda parse, right, function. You have used it in the beginning of the live, I believe. I really think it's, I mean, to me, it's more intuitive to just write the textual notation.
Yeah, for the pedagogical, maybe it is. It's just this representation is good for representing terms themselves because it's a canonical form, right?
Yeah.
Just a single way of representing a lambda term.
Yes, it has this benefit. I like it for that, but for learning, I think it's very confusing for the human
Yeah.
brain, perhaps. The tree notation, I also like it a lot, and it's very similar to how interaction combinators work, so I also like that one. Yeah, that's beautiful. That's, to me,
Easier.
much easier to understand. Yeah,
Okay, what is the correspondence between this tree and this thing here?
good question.
I think all the add symbols, add nodes, and the tree are the dots. You can count how many those are there. And also lambdas. So it's lambdas plus add symbols. Those are the total, all the dots there.
One minute. I am really confused. So, okay, so in this tree, there is function composition. That's the ats. That's the binary piece here. What is this? C. That's a. Is that okay?
So is that like a lambda itself, right? It just refers here to lambda by its argument.
Okay, let me start with something really basic. Okay, let's get the tree. Okay, there's one of those. Okay, so now let's just do, just for me, my understanding, nest list of this guy, and that's going to be a bunch, I would assume, I think I had that before. That's the thing that goes off like this, right?
Yeah.
So each composition adds, that's the lambda, that's the head, and that's the body of the lambda on the right.
Yeah.
Right?
Yeah. I wouldn't call it a composition, it's just application. They're really different operations. One is like also associative, I guess.
Each of those letters like B with the B below it is an identity function, and you have like many applications of the identity function. That's what's going on there.
Sorry, in this case here, but this, because we're basically just composing identity functions here.
Yeah. No.
Mhm.
Yeah.
Yeah. Okay. So I'm sorry, I'm still confused here. So
I
this,
like the alphabet notation. I think the De Bruyne is also difficult for, as Vic was saying, the human intuition behind it. But
Yes.
we can try to
perhaps we
okay,
can.
alternate.
let's look now at the let's see, how do we get the alphabet version? We got this version here.
It's the parse lambda function that you use it.
Yeah, we can try parse lambdas.
Yes.
Just typing out the text form.
Victor is the most, I mean, for a modern fellow, he is the most text-oriented of anybody I've seen in a long time. The, it's, okay, let's see. Well, I'm just trying to understand this. So, whoops, what did I do wrong here? Tag.
Remove one bracket at the end. Oh, in the middle.
What?
Yeah, that's fine.
Okay. So that's that. Now, if I were to say lambda 2 applied to this, I would still get, say, lambda 2. What
Well,
the
that
heck is
well
that?
that 2 now is a free variable now.
Yeah.
So it's just basically say ignore the argument.
That's evaluating, isn't it? Shouldn't we just convert it to an unevaluated form, just the actual lambda expression? Well, am I wrong?
Okay, this is super confusing because that just evaluated, as we've said a bunch of times.
Yes.
All right.
Evaluates.
Let's do some basic rheology. We've got this enumeration mechanism. We don't have a great way to represent these lambdas, but let's see the evaluation chain. How do we do that? That is the beta reduction chain.
Yeah.
For a given lambda.
That's right. Yeah. Well, there's another way of visualizing this.
Okay, what is it?
But I don't know. It's not in the Padlet. It's like what we do. Is it prototype version that you're using?
No, but I could start a prototype version.
Actually, don't worry. I can just send you this thing. It should work.
Okay.
Try installing this Padlet. It's those diagrams that we reviewed the other day. You can also represent this lambda expression with those diagrams too.
Okay. What am I going to do once this loaded in?
You just do two diagram. Just give there's some documentation knitting together happening. It happens when some documentation is being built for some reason.
That's not good. Really? Should I continue waiting? What's happening?
Oh, just abort it. It's never really gonna load now.
What is it doing?
Well, it was installed as just some kind of front-end thing happening underneath. Broke it.
So because it thought it needed a new version or something. Well, look, we just killed everything here. So let me just restart this. Okay. So can I run this now? Can I run at least process theory loader?
Yeah, I think so. Maybe not. Try installing it again. Hopefully it's gonna work second time.
Okay.
Why is it not? I don't know, I'm confused.
Well, let's figure it out. I mean, should I run the prototype build? I can try this in the prototype build.
Can try without the loader, though I think that's the way it loads.
What do you mean? Without the loader, how could it
Just
come
process Fury. Just process Fury.
Oh, I see.
Yeah, weird. Oh, it says that it's incompatible, right? It's not even the prototype version. You have also 14.1, I think. That's the problem. It needs 14.
Should I be running 14.2?
Yeah.
Okay, but I don't need the prototype version because I would prefer not to
okay.
run the prototype because
Yeah.
it's likely to be stable.
Any 14.2 will do.
All right, let me start at 14.2. Let me open this notebook in 14.2. Right. Kill that. And then let me. There we go. Needs this. Scroll down here. Why is it taking so long? Okay, something worked. Process theory loader, you said.
Yeah.
Okay.
Nice.
We're alive. Okay.
Okay. So just take some lambda term and try two diagram. It's a bit more confusing.
What the
Yeah.
heck is that?
You can start with less
Victor
simple.
loves these, but I don't know what the heck these are. Okay.
You can also try turning them into a grid. So there's a diagram grid function that you can apply to this. Yeah, you need some simple lambdas first.
Okay. Well, let's try it with a very, very simple thing. What does this mean? Well, okay, so I think I should always use diagram grid, basically.
Yeah.
Okay, what are those names there?
Now you can, I guess there's a way to remove those. But
Yeah.
The option?
the option is, I think it's something like what maybe via arrows goes to false. Oh yeah, no.
Well, just look up.
Port labels. No, it has to go like to the diagram itself. Try port labels goes to false.
In the diagram, in two diagram.
Yeah. No, in the diagram grid, I guess itself.
In the diagram grid.
Yeah. Not the plot labels, but port labels.
Oh, port labels.
Port labels in a string.
Better. Okay. So let's just take a look at our quintessential collection here, just to give us some sense of what this is roughly going to look like. Does this have sizing options?
Yeah.
Well, maybe we should do it without the sizing options first. My gosh, what's it doing? Okay, is this Victor's territory? Does he understand all of these? Maybe. Oh, we can't hear him.
It might be very helpful to convert between each time we have an expression, the De Bruyne, and then the standard way to look at it as well.
Yeah,
Okay,
sorry.
Go ahead.
I'm slightly confused by the handling of variables. You just make a circle.
Well, yeah, in a way, yes, it's a bit confusing, but that's the only way I kind of.
No, it's fine. But like, how do you know which variable is bound to which lambda? That's
Well, from the diagram, maybe it's hard to tell. It's just like basically how you knit them together into network is very confusing. But underneath is just a bunch of sub diagrams.
and the triangle is an application.
Yes, that's
Oh.
the only non-confusing thing here.
Got it. Makes sense.
Okay, let's just try to understand one more time, and then we're going to start looking at the dynamics of these things. Okay, so the different colors are effectively different De Bruyne indices, is that right, or what?
Different labels. You can add a plot label and actually show the label on top of those diagrams so we can compare. You can even do colorize lambda so that it also takes the same, has the same colors.
Yeah, there.
Yeah, plot label.
In a string.
Well, just the usual plot label. That's the graphics option.
True.
Hash. No, just hash. Right? It's just maybe colorize lambda hash. No, just hash without any function. That's the actual thing that we're trying to visualize. Right? That's the lambda term itself. Yeah, you can colorize it so that it's also colorful.
How do we do that?
It's a function called colorize lambda.
Oh, I see. Okay, so you're just saying colorize.
Yeah, just so that we can see them side by side. The diagram and the term. The colors should also match. Ideally, I think.
I don't understand how this one here, why did it apply to this? How does it know to apply to that?
Well, here it doesn't know. The diagram, this kind of diagrams doesn't know which one is the body until you actually apply it to anything else. So it's like an inert term without application. It's not wired together in any way.
I am really confused here.
So basically, lambda terms that doesn't have any argument, just inert lambdas, they're just sitting there. So they're not connected to anything.
I mean, if the goal is to better understand the lambda calculus, I think perhaps we should not focus on diagrams right now and just
we skip
go
them.
to the textual notation. I mean, that's just me.
Well, listen, I never managed to find a diagrammatic notation for combinators either that was understandable. So, yes,
No, I do think like the interaction combinator notation is very good to understand it. But like it's a little bit different from how it's handled there, so it will be a little bit difficult to make sense of it without the variable links.
We can try like applying lambda terms to some x thing so that it always has an argument. Maybe it would be better.
Okay, well, let's try this one here. Okay, so this here, let's say in here, we are saying two diagram of thing of x, and then we'll say of x here, right? Is that correct?
Yep. So there's no free floating lambdas now.
Okay, let me see.
I don't understand this at all. Why are there two circles there?
Yeah.
Well, those are some circles, like they actually can be reduced to just wire. They're not necessary there. If a circle has a single input, single output is just acting as an identity, so it can be reduced to a wire.
All right, let's zoom out a bit, and let's start looking at these things without trying to understand every individual lambda term. let's simply ask questions about, I think we can ask, let me understand the reduction. Can I see a reduction happening, basically? What's the right way to do that?
Oh, there's a better reduce and there's a eval lambda, which has just different strategies essentially.
Okay, but
Evaluating lambda.
and where's the multiway system?
Well, multiway system you can do it like by beta reductions. You can do Nest graph.
Let's do it. Okay, so let's make a beta reduction multiway system. Okay. So can I see one? How do I get one?
So you have beta reduction functions. You just literally use it in the Nest graph.
Okay.
Yeah.
Okay, so let's take a fairly simple lambda term, like this one here. How do I label this? I want vertex labels.
Yeah, automatic or something.
Okay. All right, so if I now start evaluating the multiway graph, if I enumerate lambdas of 1, okay, I only get that. If I enumerate lambdas of 2, I'm going to get this. And let's go ahead and run the multiway graphs for all of those. Did you do that already?
Maybe.
Do I have to do, let's just do, I don't know, how many steps? 10 steps? That's surely going to be enough.
Sure.
It says.
Well, so some of those lambdas are actually non-terminating. At least one, I know.
Then that's a bad idea, isn't it?
No, it's just a constant term. I think it's just it's still okay.
Okay, so let's put labeled here. Okay,
You should apply it to X. Maybe it's more interesting when you supply a default argument.
Okay, so let me understand this. So most of these just reduce to some kind of X thing. So some of them, okay, this is a non-terminating one, a trivial non-terminating one. Is that correct?
Yeah.
Okay, so here, this goes through a few steps and we see, I mean, this is a strong confluence story. At every step, the diamond can only go one step, right? And then it has to converge.
It's not strong confluent. Just confluent. It's
Just
not
confluent.
strongly confluent. Yeah, just confluent. It's
but
paths of different length.
They can be?
Yeah, they can.
If you use interaction combinators.
What's that?
If you use interaction combinators, if you do like optimal evaluation, then you get strong confluence. But like just using the lambda calculus itself, you only get confluence.
Okay. All right. So as a very operationally oriented guy, I'm going to do the following.
Me too.
So let's do this, and let's just say, rid of the vertex labels. I'm going to live slightly dangerously here. I'm going to say, enumerate lambdas. So I have to run this in parallel.
Well, there are too many of them. Well, just rendering them is going to be a problem, I think. So you should really stop it. Too many graphs.
All right, well, okay, so let me just see this in 2. I shouldn't have labeled them. Okay. Am I able to, can I say canonical graph of all these? So I can get the number of distinct, so let's just say.
Delete duplicate by canonical graph.
What's that?
You can do delete duplicates by canonical graph. That's useful.
I'm just going to do this. Okay.
That's cool.
What's that?
That's cool.
All right. Let's do the next level up. Do we need to fire up the parallel machines? Nick, is it going to be useful?
I don't know. Depends how good at those right now. How many lambdas are there? The free. Is it like already in thousands or hundreds? Oh yeah.
44.
Okay, that's a number. That's quite a number of them. Okay. Let's fire up the parallel. Whatever. Hopefully all my machines are online today. Oh, come on. Don't. Why is it?
Do you have to like install packlets on the packlet on all of them?
Oh God, yes, we do. Do we? Or does it?
I don't know.
Let's try it without that. I think it may just work.
It's
I
just
mean, the good
better
news is
reduction.
that in version 14.2, which I'm running here, maybe I need to set some option, but it's supposed to launch in parallel now, which it clearly isn't doing here. Okay. Let's live less dangerously. Let's just do the 2 case. Let's say parallel evaluate, parallel map. What the hell is that?
I think it doesn't know about beta reductions or something. So you have to parallel evaluate packlet install. I don't know.
Yeah.
Otherwise, just nesting but beta reductions as a symbol.
Yeah, I understand. Parallel evaluate. Which one of these? I have to do this one.
Just
here.
the top one.
But I need the once only parallel evaluation, right?
Yeah.
Do you know how to do that?
Or is it by default in the ones?
No, it'll
Oh
do
yeah.
it. I only want it once per machine.
I don't remember how to do it. I've seen it somewhere.
One kernel per machine.
Yeah. Something like that.
All right, let's try this. It took a while before, didn't it? Come on. Okay.
No.
What the hell?
Oh, it only works. Remember, it only works on 14.2. Oh, is it? Hold on. Lambdas are not. Lambda should be the problem. I don't know then.
Oh, hold on. I don't understand why this wouldn't work. That's crazy. It's the same machine. Oh, I know what's wrong. I know what's wrong. I know what's wrong. Stupid, 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 stupid mistake. Stupid mistake. That was what we wanted to do per machine is the Packlet install. But this we want to do on every machine. Right?
Right. Yes.
On every core. On every core, we have to load that.
Huh?
Why can't it find them? Oh, come on. I don't understand what's happening here. Okay, we did a Packlet install. How can we check that we've successfully installed the Packlet?
You do Packlet find. And if it's not an empty list, then it's okay.
You know, somehow whenever we do these things in parallel, this is what Victor has to solve with his whole technology stack. Is doing things in parallel has got to be trivial.
Yes, that's the plan.
However, this is, you know, one of the awkwardnesses here. We're dealing with heterogeneous environment of machines. Okay, what happened there? Some machines didn't install the Packlet.
Yeah, it looks like one set.
Well, many machines there didn't install.
Try
It's
again.
still very cool that you can coordinate many machines with pure expressions like that. I was not aware of that, and that's very cool to watch.
Yeah. Yeah, the only problem is it isn't working here. That's the
Happens.
okay, wait a minute. If I just do a Packlet install across every machine, that's not going to work, right? Because the Packlet install is installing centrally on each machine, right, Nick?
Yes. In the current kernel.
No, but it doesn't care whether it's a kernel. Wait a minute, the current kernel, are you saying, should I have just done a Packlet install? Should I have just forgotten about the one kernel per machine here? Or is that going to cause even more trouble?
I mean, it doesn't need to install on every kernel on every machine.
It may be just connection issue, maybe just some outdated Packlet site. It doesn't just know
How
about
appropriate
Lambda.
is available to download for many currently
Can you do? I know maybe what's up. You should do Packlet install per machine, but you also set the option like site updates or something like that. You need to update a list of Packlets because they just maybe it doesn't they don't know about new Packlets being there.
I see. Okay. Well, what was happening here? We need to do that. Okay. Just tell me your idea for what to do, and then we give up if this.
Yeah, just Packlet install with an option update sites goes to true.
But that's just one kernel per machine, right?
Yeah, I think that's fine. You don't need.
Not update Packlet sites.
I think they both
Okay.
work. Maybe update Packlet sites. I'm not sure. Yes.
That's
Like,
one I used.
Packlet sites.
Okay. Now here, then after that, we just say, oh God, we have to start all the machines again. But
There are a lot of machines.
well, I finally got my AWS setup working. That's really a cool thing. We can do that if we just say remote batch submit and then just give an expression and it just runs it on a bunch of, you know, Amazon cloud machines. I just have to like to make sure that I know what I'm doing in terms of how many machines it has. Otherwise, I'll find I have a giant bill. So that's the advantage of using my own machines, is that they're
Limited, not auto scaling.
okay, all those Packlets are done. Okay, so now let's do needs here. Let's run the needs plus all those machines.
It's gonna be 100 nulls. Yeah.
Yep, all good. Okay. Now, why didn't this? Oh, that's on the parallel machine. So I now need to do this here on my local machine, and that will all turn black. And now if I run that, ta-da, beautiful. Okay, different machines got different things. We can now ignore what machine is running it. We remove that. And we're all good. Okay, so now let's do the counts. That. Ta-da, there we are. Okay, let's live more dangerously. Let's try and do the next level up. Now, or I could do 2, 2, couldn't I? If I do 1, 2.
No, 2, 2 is the default. You
Oh.
already did. So that's already the 2. You can do 2, 3. I think it's less than 3, 2. But not sure.
Are there going to be some that are really hard? Because we're at 992 out of 1140 evaluations there.
Oh, I got there quick.
What's that?
Yeah.
It got there quite
maybe
quick.
a bunch
Yeah.
of trivial ones.
I don't know. It's just weird. Maybe because there are some that actually exploding in size. So 20
Must
steps.
be.
Yeah, 20 steps may just produce very giant terms.
Well, it just went up from 993 to 996, but I don't think this is going to work. Let's kill it there. It will listen to me. And then what do you think? We should maybe make the 20 smaller.
Yeah.
Because we'll easily be able to see if they actually terminated. Because the confluences, all bets are off when it's non-terminating, right? There is no similar thing to confluence when it's non-terminating. Is that a true statement?
I guess.
When you say similar, what do you mean by similar?
Why is this not
Canonical.
This is the same thing again and happening in version 14.2. Damn. Okay, I'm gonna have to kill the old kernel. Whoops. Annoying. Okay, well, let's just do 5 steps here. Sorry, we got to. This is supposed to be blindingly fast now. Maybe there's just some option. Does anybody know? Can anybody look up because there's been a bunch of correspondence recently about this parallel launching and parallel machines. And do we know if there's an option for doing this? Okay, let's take a look. All right, come on. This is like the most annoying thing. I mean, the good news is that we're ramping up pretty powerful machines here. So, all right, let's just find out. Enumerate lambdas 2, 3 has 24,000 terms. Okay, so let's just do 5 steps. You know what? I'm going to put a time constraint. Is it worth me putting a time constraint around here? Nick?
Yeah, why not? Yeah. It's a good protection against this kind of things.
What would you give me? 30 seconds or something? 100 seconds?
No, 1 second is no, that's too much. Just do something like 1 or 2 seconds. Maybe 5.
Right. Aha. Well, there are some criminals here.
Yep. Wow, look at that.
Wow.
That's
Welcome
beautiful.
to Ruleology. Story of my life. Lots of little pictures of weird computational systems. All right, let's see what's going on here. There's some pretty funky things going on. What are those guys? Does that surprise you?
Yes.
I
That
mean, I
actually
would have
does not make
expected it was
sense to
just,
me.
what's that?
That does not make sense to me. It means that there is a term that reduces to itself and then reduces to something else.
Yeah, it doesn't make
Well,
sense.
it's like remember that term from the small lambda set that repeats itself, right? It's essentially if you have that term inside some other lambda term that actually can better reduce to some normal form, then it's like if you continue reducing that one inside, that's what we get.
Well, yeah, so the beta reduction is doing what? It's changing, it's just circling around a lambda, an equivalent lambda. Is that correct?
Yeah.
What's the explicit? Okay, we've got all kinds of things going on here. Okay, so let's just
Can
take
we
a-
extract those lambda expressions from the pictures?
well, if I'd done this properly, yes, but we didn't do it properly. So let's just get, okay, so for each of these pictures, let's also get the minimal lambda term that corresponds to that picture. Okay, let's display that. Or at least let's make a click to copy of that. I don't know what's going on with some of these here. We really, you know, I mean, some of these, let's look at the first one. Okay, hold on. All these enumerate lambdas, these are all have the same leaf count, is that correct? What's the, let me just
Oh,
look
they
at
can
them.
be less. It's up to 3.
Okay, so
So
let's prune them by leaf count, just so we have the simplest expressions. Let's say counts of leaf count, oops. Okay. So let's just do this by leaf count, okay? So let's do group by of the enumerate lambdas by leaf count. Okay, and then let's do, I assume that that is going to give us a thing which is an order of leaf count. Yeah, I think so. Okay, so now what I want to do is I want to do the same guy here by order of leaf count. So let's do this, oops, that there. And what I want to do is do that onto the group by of this. And each one of those hash onto the group by thing there. But let's actually only do, let's take the first 5 of those. Okay, so these are in the successive, I'm just going to put, I'm just going to do this just for the hell of it. Okay, so these are successive leaf counts, right? So I'm looking for the first one. Okay, so up to 6, nothing very exciting happened. So let's try this up to, let's try up to 8. Okay, so we're on a hunt here for the simplest case where something funky happens. Okay, so we've already got something slightly interesting happening there. Okay, there's our first grower without bound. Okay, so most of these are fairly civilized. I mean, we've got some that take a while to evaluate. We've got the busy beavers of these lambdas. And then we've got some that just blow out. So let's find out. All right, so first question is we want the busy beaver of each. It'd be kind of interesting to see the busy beaver of each of these cases. So let us go ahead and, I mean, I could just do a take largest by to find that. And then here, well, okay. Have you looked at the first non-terminating one? Let's find that first non-terminating one. Should we do that? So
that looks like a dumbbell. Right?
Yeah, well, here, let's do this. Let us say, in the counts, I need to put the click to copy on the outside, right? Because if I do the count, what I really want to do is I want to say the count. Yeah, what I want is I want the representative, the first representative of each thing.
Mhm.
So instead of counts, what I want to say is here.
Well, when you canonicalize, you already remove the actual expressions.
I know. So what I want to do here is I want to say canonicalize that, and then I want to put, after that, I want to put the original expression, hash of x, there. And now instead of counts, what I want to do is I want to say here is I want
Counts
to
by
say,
first.
what's that?
Counts by first.
Yes. No, but I don't just want counts. I want to, because I want to get the actual first representative. So I want to say gather
Well,
by.
then,
What's that?
oh yeah, but then you could have just
Gather by that first. And then for each of those, what I want to do is I want to say,
maybe you want group by so that it's an association. You could see.
well, wait a minute. What are you suggesting? Because what I want to see is, I want gather by, because then what I want to do is I want to take for each of those.
But when you do gather by, it's not going to show the actual graph already. You're going to remove the graphs. So group by, and then the third argument to group by is just first, right? Again, or map first.
No, wait a minute. That's giving us, it's grouped by the first. And that's going to give us the graph. And then all I need to do is apply to click to copy, I think. Right? Because
you need counts also, right? You need to count things. So group by is just going to produce an association of where the key is the graph and the values is all the lambda expressions together with the graphs, right? You need to compute the length of those and also extract the first candidate.
Yeah, I agree. Okay.
So that's the third argument to group by.
So what do you think it should be?
Should be like a function which makes a pair, which is the length, and just extracts the first expression. So it's like part 1, 2, something like that.
Well, wait a minute. First expression is part 1, 2, and then we want to say arrow length
of hash.
Of hash.
Yeah, something like that.
Okay. But now instead of doing that first piece there, instead of doing hash 1, 2, what I want to say is, why is there an arrow there? I don't understand that.
So it's an association. You're making your keys are canonical graphs.
Okay. All right, fine. So now what I want to do, well, this is good enough, actually. This is good enough. This is fine. This is useful. We're then seeing the lambda expressions there. Okay, so let's go ahead and see our first escapee. Okay, so that lambda expression, for example, has that evaluation graph. All right, there is our first escaper. By the way, we didn't have, yeah. Okay, so we got these. And by the way, we probably should compute the busy beaver one of these. So the longest finite lifetime. Well, we're going to get that in a minute. Let's get the longest finite lifetime ones, but let's first of all get this guy. Okay, so let's look at this one. What is actually happening in this one? Oops. Okay, how do we do this? So we need a nest graph of beta reductions. Is it beta, what is it? Beta reduction?
Yeah, beta reduction.
Okay. Of, let's say 3. Okay, and now let's say vertex labels. Oops. Actually, I'd like to try using one of your other, what do you think would be a useful thing?
What do you want to use?
Well, let's just try for the sake of something. Let's try your, what was your thing? Lambda diagram?
Yeah. So let me make you a nice vertex shape function for that.
What do you think? Rather than a vertex label?
Yeah. You can do it yourself. It's like just making an inset.
Okay. All right, vertex shape function. I always get confused how to do this. Can you tell me how to do this?
Yeah, so it's a function. So wrap it with function. Make an inset.
Well, it's got to have an argument here.
No, it's just gonna ignore it. Ignore the argument. Just inset, just the body. So that's lambda diagram of #2. And comma #1, #3.
#1, #3?
Yeah.
What about the vertex size?
Oh, let's try it like that first. Yeah, let's reduce the image size. And maybe do framed around lambda diagram. And also performance goal also helps. For the graph.
Okay, hold on. Let's do a framed here, and then this thing can have an image size. Should I do the vertical height image size, or should I do the
Oh, that's fine. Do the performance goal for the nest graph. It's gonna make edges nicer. Quality.
Well, I don't consider this immediately helpful. We're going to try some other visualization techniques here. Let's squash up the aspect ratio here. Okay, I'm going to go one more level. Let's see, how do I want to do this? I want to do image size goes automatic. Let's say 30, height 30, no, height 20. And then aspect ratio 0.4. Well, it's not wildly helpful for me to see what the hell's going on. Should we try a different visualization technique? Should we try lambda smiles?
Oh, sure. Well, let's try it. Yeah, those are tricky because of the font.
Okay. Any other visualization technique that might be helpful to us here?
Well, let's just try those trees then, and I think we're.
Well, actually, I'm going to try something even much simpler than that. I'm just going to try writing here the leaf count of each individual thing, right?
Sure, you can do that. I think the tree would be nice. like without any labels.
Yes, I'm like just waiting to see the trees.
Okay, well, let's see. Look here. Look here. Notice that they're not all the same size. Right? There are different
Yeah.
sizes of. So in other words, there's a reduction here. If I get rid of, I don't even think I need. Do I need vertex shape function even? I could just say here. Vertex label arrow, vertex labels arrow placed of, well, x blank goes to placed. Do I need a paren? No, I don't think I do, but anyway, placed of leaf count of x comma center. The reason I'm procrastinating on the trees is because we have to deal with, hold on, let's just see that. Oh, come on. Hi. All right, there we go. Okay, so what we're seeing there is that we have kind of a range of different sizes here. So this thing is, okay, 9, 7, 8, 12, 16. Okay, I'm going to go one more step. Okay, so this is a pretty complicated object. This is not just, trivially exponentially expanding. It's doing something more complicated. Okay, let's see the trees. So what do we want to do here? We want to say each individual tree, Nick, what's the story for the trees?
Well,
Because we want them without labels.
yeah. Well, first do lambda convert to tree, then wrap it with three, something like three labels. I don't remember what.
And then tree of this. Tree element label, right?
Yeah, three element label goes to none, I guess would work. No.
Okay.
I'll try underscore arrow none. Maybe it requires a pattern.
Okay, let's get rid of the @ signs.
I think
We
I
need
do
to-
it with
what's
some
that?
kind of shape function. Yeah, hold on. Let me see.
I mean, I suspect if I just said tree graph here, or tree, what would happen? Let me just see what happens if I just say,
Yeah, that also would work better.
okay, now I want to say here, I want to say image size goes to, I don't know, 40 or something. And now I want to get rid of, how do I get rid of the stupid arrows?
Edge shape, edge style, edge, something like that. Edge style.
Actually, I know a hack for getting rid of them, which is undirected. Undirected
graph.
Okay, there are the trees. Well, let's go one more level. So it's not necessarily helpfully. Oh, shoot. we need to say in tree graph, we need to say graph layout goes to
Tree embedding.
Is that going to work?
I'm not sure.
No. We could say layered graph. Oh, come on.
Try just layered layered embedding without diagram. I think it's
Yeah, our audience is asking for image size 16 so that they can actually see what's going on.
Well, let's just hold on. Why are we? Why? Well, this is nice, but why?
they're natural trees now that grow.
Yes,
This is
I
actually a
understand.
very good visualization. Like I can actually see what the terms are, even though like there's no namings. But like it's very clear from the reductions what are the variables. I love this visualization.
Okay, you can explain it to us because, okay, hold on. Let me just why did we get 2 copies here? What the hell's going on here? What did I just make? I missed.
Just remove them.
Okay, hold on. How do I get these to tip the other way up? Do I go reverse graph?
Oh, there's an orientation for the embedding option, right?
Oh, there
So
is?
graph,
What is it
so
called?
your graph layout, you do it in a list, and then orientation, arrow right or down, bottom, I guess, bottom or top. I don't know. I don't know how. Just try bottom or top. Try bottom.
Well, no, I think I should try top. And we will.
Hmm.
Okay. All right. So now you probably get those ones at the bottom there. You probably get these a little bit bigger. Hold on 1 second. Image size goes to, let's say, 60.
You can make size proportional to leaf count.
I know. Yeah, right. Yeah, we could do that. Let's do that. Okay, but we could just go another level just for the hell of it. Maybe. Well, maybe not. Actually, you know what? If the main nest graph doesn't have, if that main nest graph,
I'll try this new state embedding thing.
oh, I was just going to do spring electrical. Unhelpful. Somewhat unhelpful. Well, actually, it doesn't help that I've got the silly aspect ratio here. Slightly more helpful. I kind of feel like with these trees that there's some representation that just tells you kind of the depth as a function of position or something. And that should give you kind of a simpler profile of what's happening. But okay, so let's just look.
Like maybe not now, but improving the visualization would be just actually highlighting what the beta reduction, where it actually acted.
Hmm.
Yes. Yes, that's a good idea.
There was a question in chat here for Victor asking if there was something you could say about the depths of these things. There was some kind of like intuition about that.
Well, let's just look at the depths. Let's just run this. That was the leaf count. Let's run the corresponding thing with depth.
Sorry, did you say what? The dips?
Depth. The depth of the. Well, look.
I have some things to say, but like I don't want to interrupt because it seems like we're learning a lot. So
Well, okay, but okay. One thing we just learned is that the depths vary a lot.
Hmm.
Okay, some are depth 8, some are depth 2 here. Okay, Victor, go ahead. Should we tell me what to, should we look at this picture here? Is that the most useful one?
Yes, I do think it is. Um, One observation that like initially I just wanted to make is that um, it's interesting because we have so many shapes of like how things can reduce to each other when you're talking about the lambda calculus and when like you're doing just like the interaction combinators, it's just like a boring diamond. You don't have like this structure, those kinds of terms that you have here. But like this term, I think that all the small terms that you are gonna find that are looping like that, like exploding, they're just variations of lambda x of x applied to x because it's a lambda that receives a variable and then clones that variable and then applies it to itself. So if that other variable itself can make clones like that, then you get that behavior where like things are expanding forever. So for example, here like you have lambda x uh, of x applied to x, and then you have another term that I believe is lambda x of x applied to x applied to x. And then like you have something that makes 2 copies here and something that makes 3 copies here. And you apply that thing to that thing. So now you have something that makes 3 copies, apply it to itself, and then you have like those, like this kind of behavior. And I suspect that because like the last term is the one that has 3 copies and the middle one has 2, I do think that what's happening is that like you have 2 copies here and then 3 here, so that's why like to the right you see more and more terms. That's like what I think is going on. Does not mean that's what's going on. And I do think that you're gonna find many terms in this enumeration that are looping, and now of them I believe you have like this term there that's the lambda x of x applied to x. Here it's rendered as lambda 1 applied to 1, right? So that's what I can learn from this like initial visualization. I love that. I would love to see how it would look like if we did this enumeration for interaction combinators. I actually would love to see that
Well, let's
because
find out. Let's find out. It's going to take, we probably
we
can't do that in real
can't.
time. It's probably going to take a little bit longer to program this, but
I I don't
you
think you
have
can
multiple kinds
enumerate.
of reduction, right, Victor? There's more than one kind of reduction. There's several rewrite rules for interaction combinators, whereas here we're just using beta reduction.
Well, that's the main one. You don't have to worry about any other.
Yeah, that's actually not totally true because it's true that's only beta reduction, but beta reduction is doing 2 things. That's like substitution and copying, right? So in a way, all that like the interaction combinators would be doing is separate that like monolithic operation in 2, and in the end you get like the same terms, something very similar, but like with this boring structure that you don't have those wildly different reductions going on. This structure is that the reason you have so many different images is exactly because you unified those 2 operations in one. So things get crazy, but that's not natural to me. That's just, I mean, visualizing it like that makes it so clear things that use it were already intuitive to me before. That's why I love it.
Okay, so okay, for another, who knows how to get the number of elements at layer n in this picture? How do we do that? Nick?
What is it well, if you have a tree, you can just count with like something like tree level.
But this is a nest graph.
But you can turn it into, oh, I see.
This has mergers. I just wanted to count the exponential growth. So we could do that by looking at the number of nodes. Don't we have some foliation thing that will separate this into layers?
Well, we should
can
have.
set-
I
what's
can't
that?
immediately recall. I don't. I mean, I can't immediately come up with a good, quick solution for it.
Okay, but if we just ask the vertex out component, right? Of the
Yeah.
initial thing.
Mhm. With an
Vertex
X.
out component of that graph, comma, the initial thing.
You forgot
W1.
the X.
What's that?
You forgot the X one.
Okay, so that's the vertex out component at level 1. So let me just evaluate this one time. Okay, so here, let's say n, and we want to say length of the vertex out component of n, and then we want to say table that.
Shouldn't be an n in a list.
Why?
Just like
did I
that
do?
away. No,
Oh, I see what you're saying. To get the layer.
yeah.
N goes up to, well, let's say 6. Okay, so that's our, so let's try doing this up to 8, for example. And that up to 8. Okay, so that's our growth. And actually notice that those numbers are very similar. Well, let's just go a couple more steps. Let's live dangerously. Let's go to 12.
Nah.
Well, maybe that's not well. Okay. Let's not go to 12.
Yeah.
Let's go to 10. Come on, that's going to work.
I think that's gonna work.
What's that? It's only
It will-
exponential, isn't it?
I don't know, it jumped like from few hundreds to 4,000, so I don't know. Like this is already should hit like hundreds of thousands. Maybe.
Yeah.
Yeah.
Okay. All right, so let's do ratios. Oh, bad. I thought it might be doing that. It's increasing faster than exponentially. I bet it's like something like these Bell numbers. I've seen those before in these things. Okay. Is that what we would expect if it's a thing applied to, if every pair is replaced? Yeah. That's the kind of thing we would expect. If every pair is replaced by a triple, so to speak, that is worse than exponential because every single pair is replaced by a triple. So as you have more pairs, it's not like everything is multiplied by 3/2. It's like everything, I've seen these before. For what it's worth, I remember this in a physics project thing that shows up. Let me just look here just for a second, just to remember this. But okay, then I want to come back to, okay, hold on a second. Let's see. Well, whatever. I remember that there's this happens, that the thing happens here. Yeah, I mean, there's a bunch of things like, oops. For what it's worth, there are rules, there are hypergraph rewriting rules that also have this property that they get worse. Or whatever. I don't specifically remember how this works, except that I do remember that there are increases that are faster than, well, whatever, doesn't matter. Okay, so it's faster than exponential growth. All right, what else can we learn quickly about these things? So we've seen, we could work out the busy beavers. What else are we going to learn here? I mean, we're just seeing a bunch of reductions. There's a question, I guess, of how, well, okay, for interaction combinators, Victor, what is the, you presume, obviously, if they're universal, there must be things that don't terminate.
Yeah.
But isn't it the case that, I mean, they can't be purely deterministic. That is, they can't have no multiway, no spreading in multiway space. Is that true? I mean, there must be different reductions that give different, or is it the case that the reductions are always, that you always just have diamonds? That seems very, very surprising. That you can, that the things will just have a diamond on every step.
So I would love to see the visualization for that, but what's on my mind is that to have just like borrowing diamonds everywhere, and then you have some terms that return to itself, and then you have some terms that the diamond goes on forever, but it's always a diamond, right? That's how I see it. I'm kind of confident of that, but it could be wrong.
So you
That's how I
say it
see it.
basically makes a grid. Your belief is that the worst thing it could do is make a grid, that it can't, for example, do this exponential growth thing that we're seeing here. Is that the claim? I am skeptical, I have to say. Nick, do you have enough?
Yeah.
Go ahead.
Sorry. No, the thing is, one thing that's perhaps a little bit confusing in that lambda calculus version is that a lot of things can happen in a single step. So what's a step, right? What's a line there? And in the lambda calculus, many things can happen, and that even makes it a little bit more difficult to visualize. But on interaction combinators, there's just one thing that can happen in a step. That's O1 reduction rule, right? So yeah, I do think that kind of confidently, but like could be wrong, but like 99% confidently that like the only thing that happens is that it grows like a perfect diamond, and if you do the same kind of computation, you will never see this kind of exponential growth because you like are plotting by number of reductions. So that can't happen. I could be wrong, but that's
Okay, so I'm going to make
how I
a guess
predict.
that it is not a simple grid, that the grid can end up with multiple folds effectively. That while locally it might be a grid, that you can still have, you can have grids of, you know, instead of just being a two-dimensional grid, that it can be a grid that folds out in any number of dimensions.
No. Like if you do the reduction plots, like those trees, I think it's just like literally like just a pyramid. Like I'm not sure if that's how you pronounce that, but that's just the only image that I can see emerging from that kind of system.
Okay,
Yeah,
so
Literally just
I'm
like a
guessing that it
big
isn't
triangle.
that. I'm guessing that, so what you're suggesting, okay, is that it would be something like a grid graph. Let's say something like, you know, I think what you have in mind, if I'm not mistaken, is something, if I do this and I say, you have in mind something like that. Is that correct?
Yes, but like the infinite terms, is that how you pronounce it? But like the terms that don't end, it just never gets like in that part where it
Yeah, right.
shrinks
It
down.
just
It just goes on
goes on
forever.
having
Yeah.
lines like that.
But I also think there will be some points that go to itself,
Okay.
right?
Yeah. Okay, so I'm speculating that it doesn't look like that. I'm speculating that instead it comes out that it's like a grid, that where at this point, instead of there being just two possibilities, there can be n possibilities here.
yeah.
That it still merges, but that there are n possibilities there. That's my guess. But Nick, do you have the technology to just try this?
No, but
Oh,
I do agree
I,
with you. I think you're right
yeah,
about that, actually.
I mean,
I
we
had.
could probably make a model version of that, but go ahead, Nick.
Oh, I definitely seen some multiway systems of interaction nets. Maybe I can pull them off if you give me some.
So you're telling me that like in the lines, like in the horizontal line, some of those points would be merged in one, right? Not
Maybe. I mean,
quite.
I'm thinking instead, we should just try it. We should just try it. That way there's no sorry,
But I
what
think
did
that's
you
going to happen. Sorry.
yeah. Nick, what were you going to say? Do you have code that can do this?
Well, it's too complicated. I had some code that has interaction nets and multiway systems for those. They look like Yeah, because they're strongly confluent some kind of grids.
You
But
want
yeah,
to
like, you're right, because you can have multiple reductions at any point. It's not just two, so it's not
Right.
really two-dimensional grid.
right. Do
Could
we
we
have an
enumerate
as-
them?
What's that?
Could we enumerate them, the 200 kernels? Let's see what they look like.
So can I just make a quick comment? So for example, our logo, it's interaction nets that's reduced to itself. Like it's two triangles connected and like and what I think happens is that like it goes like this. Starts with a point and then two different terms and then goes back to a point. So it's not actually a triangle, it's just like this. Just a line, but with 1, 2, 1, 2. And now that you mentioned that, I think that not everything is going to be like a grid like that, because the points will merge. As you said, it's like we'll
this is
have
a
some
worst
identical
case
terms.
scenario. Is
No,
this
but
kind
I
of a
think
worst case scenario?
that it's polynomial growth. I mean, that will be the. I think Victor is claiming that it's. I think that it's polynomial growth, never exponential growth, and which might be true. I mean, I was going to say, by the way, what we did up here, way back here, we were looking at this thing here. Let's just try, for the sake of completeness, we did that for the 2-3 case. We also should probably try the 3-2 case, just to see whether there's different phenomenology there, just for fun here. Let's see, 3-2. Looks very similar. Nothing happened. Okay, let's go up to 8 again. Looks very similar to what it did before. Well, that's just a silly, messy drawing of it. Okay. Now we get some that don't seem to be converging anymore. I don't know. How can I avoid these silly things here? Is that a graph layout? That's a graph layout option inside here, right? Well, where is this? Canonical graph. Oh, that's this nest graph, right? So I need to say the canonical graph here.
Well, you can key map, because those are associations. You can key map a graph with the graph.
Onto these. No, but I have to do a map of a key map. But why don't I just put it in here?
Yeah, well, if it puts the option in the correct place, so it's still canonical. But yeah,
Yeah, I understand.
hopefully it is.
This will either blow everything up completely or work perfectly.
Put a comma.
That would help, wouldn't it?
Weird that it doesn't take an option. Where's it red?
Oh, because I know why it doesn't take options, because the canonical graph wants to be canonical. It doesn't want to mess around having options. It wants to
Yeah.
actually be canonical.
I do have a quick question. Is there a way to enumerate linear lambda terms? Sorry for.
I don't know.
Linear. What do you mean by
Yes.
linear?
I mean like lambda terms that don't use their bound variable more than once. Can you just like make a quick filter for that?
Yeah, sure, we can do that. Let's do it.
Yes, I think that would be very insightful to visualize what happens, because now all terms will terminate and you'll never have any loop.
Okay, let's try that in 1 second. Let me just try.
Okay.
This is the
Sure,
group
sure.
by of this. Nick, help me here. We want to take, I see, we want a key map
Uh-huh.
onto every element here, right? We want to say key map of graph hash graph layout arrow layered digraph embedding. Actually, I could just say layered graph, couldn't I? Is that
I
true?
think so. Yeah.
Layered graph onto, that's a key map. And I'm doing that across that.
There's an operator former. I think you can just map key map. It's convenient.
Oops.
So does it have to be mapped? Just apply it. It's not a map. Or is it?
No, it has to be a map because it's
Oh,
got
yeah.
to be on
Oh,
each. It's a map onto the group by.
but group by produces an association where the first element.
Okay, what do you think this should be? Do you think this is just layered digraph key
No,
map?
just key map applied instead of map. Just remove that slash.
Well, that one will probably terminate after another few steps. Okay, so some of these, this is very much like combinators. Some of these have complicated forms, some of them go on forever. Okay, let's do Victor's thing. So let's say enumerate.
We'll have to write it
Under-
out, right?
What's
Or we
that?
just got. I'm trying to just select it out.
Yeah,
Right.
that's what we were thinking about. Is that possible, or is that too difficult with all the De Bruijn indices?
Now let's see.
By
So
the way,
what
for Victor's cultural education, I am 99% certain that De Bruijn is pronounced De Bruijn, like that. He was
Bruijn.
Dutch. De Bruijn. I don't know. Somebody should say it with not a British accent. I don't know.
De Bruijn.
De Bruijn, yeah.
I mean, I just assume everything that I pronounce is wrong by default, so you're probably right.
Well, no, I'm pretty certain.
Yeah.
I know enough people who knew him that
Wow.
he was part of he had this whole automath project. It was very interesting. I never met him, at least as far as I know. But he was very interested in the formalization of mathematics. Worked at Philips in the Netherlands. Anyway, okay. Is there a way to do this? Is there a way to filter these? Is it just as simple as saying you only have one De Bruijn index?
Well, it would help if you tag it, like the tag lambda by default also tags each of the indices with the.
Tell me how to do that.
Oh, the tag lambda function, right? It's not going to change visually the lambda terms. You can map it over each of the lambda terms.
If you have a function that counts the bound variables of a lambda, perhaps you can just filter by like lambdas that have only 0 or 1 bound occurrence of its variable.
I don't think I have this function, but we can write one using this tag. Like if you look at the input form of those, you can kind of guess what it is. Because it's basically interpretation. So we have this lambda, and its arguments are also tagged with the same thing. So we can do some kind of counting, like inside of it, on known levels.
Wait a minute. So the criterion, what is the criterion again?
So every lambda must use its bound variable only 0 or 1 times. So, for example, lambda x with x applied to x is not a linear term because it's using x twice. Does that make sense?
Yep.
Okay.
Okay.
Perhaps it will be a little bit difficult to code that live if you don't have like a function that counts.
Well, but what about if we converted it to functions?
Well, the stacking is basically doing that. All you have to do is like map over each lambda, which is just interpretation of the lambda, and inside of it just count all the same thing with the same tag. That's gonna count the variables.
Okay, help me out here, Nick.
There's one helpful one I pasted in the chat, maybe just to elucidate an examples using pure Wolfram arrow functions. Maybe just as an example.
Is it just the same? Anyway, I'm gonna try writing it down.
Take out the triple quotes. Yeah. So if you can see what's going on there, it's a lambda term, the A goes to BB, yeah. So that's just plain Wolfram language. So you can actually write lambda terms in that way.
Right. But this, by the way, is not an example of your thing because the A appears twice, right? That's not a linear lambda. Is that true? Even though that A appears inside a subsequent lambda.
Yeah, that's true. So you need to like count the number of A's. Like if you just make
So this is, it's this lambda, there's the term, there's the first argument of this lambda, right? This first argument here. And the question is, does that first argument appear deeper, right? In other words, what we've got, Nick is probably doing this, but I could do this too, just for whatever it's worth. The thing is, it's index blank there, and then this we know we have one of those. That lambda necessarily has that as its first argument, but then its second argument is its body there. And the question is the body free of I blank? Is that right, Nick?
I'm not paying attention. Sorry.
Oh, no. Okay.
I almost wrote it.
It's
I
cool.
already wrote it.
If I can just use this to just make a small correction, just for the record, linear terms should use the variable one time exactly. So what we actually define is affine terms. Sorry about that. Just to
Fine.
be a little bit more technical.
Well, okay. So is that what you want? Let's say.
No, I want affine terms. You define it correctly. Just change linear by affine. Just
what is it
sorry,
called?
just yeah, affine. Is that how you say it? Yeah.
So
Thanks.
just for my benefit, also linear terms.
Okay.
Use variables exactly once.
Yeah.
Okay. All right. Fine. Okay. I'd like to see both of these actually. All right. I think I see a way to do this. So.
Nick gave some code as well.
Oh, Nick has code. Okay. I was going to do some crazy code with sows and reaps. I think you can just do a substitution of this.
It's just little simple cases. Just take the code and Zoom chat.
Okay.
Can use it.
Very nice. I don't know. What's this? This is. What does that mean? That's just.
We're just counting each lambda and how many variables.
Oh, that's a random lambda. Okay. All right. Fine. Yeah. Okay. So let's go ahead then of the enumerate lambdas. And this here will be okay. So all of those are linear terms, if I'm not mistaken, because they only have zeros and ones. So let's go ahead and do this. Let's say, just to simplify this, we can say values. Okay.
Can we
So
confirm?
that's the claim.
Can you also show the actual lambda term so we can look at it and confirm that it's true?
Okay.
Can you show then as strings? Oh, okay.
Strings or trees? What would you like?
strings like with the variable names,
Oh,
but
you
I
want,
can do with that. So for example, here you have a variable that's not a lambda that's not linear. It's like receiving, like it's applying one to one. So
which
something's
one?
wrong here. Um,
That one there?
yes, many of yeah.
Okay,
If
so what happened here?
All right. Let's debug it then.
Okay,
okay,
so let's look at that term there, and let's go back up here. And so this term, so tag lambda this. Okay, so that's what that
Well,
looks.
you need, I get, I don't know it. You have to add heads goes to true in the count. And I guess also in cases everywhere. Heads goes to true.
Okay, right there.
Yeah.
And there we go. Beautiful. Okay.
nice.
All right. So now let's pick out the purely linear terms. So let's say max values.
Less than or equals to 1.
Right. Okay, that looks somewhat convincing. All right, so now we want to do the same thing that we were doing before, namely one of these guys. But not just for, okay. So let's do this. So that's selected over enumerate lambdas of 2. Ah, what happened here? What did we do wrong?
Maybe there's not less than 8 things there. Up to, just to up to 8.
You're correct. Okay, so that's the, why did I do, what was I doing here? Why was I doing a take anyway? That take is silly. I don't want the take. Oh, I know, I see why. I understand why I was doing the take. Never mind. Okay, all right, so now let's keep going. So that's the linear terms. So now let's do enumerate lambdas of, what should we do? 2, 3. Okay, so there's no looping and no, okay, so let's just go ahead and do all of them. That's encouraging. Okay,
Yeah.
so right, so that's those are your affine terms. So let's do a 3, 2 here. So that may be more, that maybe you think that's more like what the interaction combinator versions of these will look like.
It's identical. I think it's gonna look the same. I was wrong about like this diamond thing because you have equal terms. So it's exactly what you predicted. Like some points in the same horizontal line will be merged. And then yeah,
Let's pick something like this. So that is probably a hypercube of some kind. Well, let's pick, I don't know, the most complicated one of these.
look, that's so much more beautiful than the lambda calculus. full lambda calculus
Yeah,
version.
it's somewhat convincing, but it's okay.
You can see how much more natural that looks, at least to me.
Yeah, no, I agree.
Yeah, yeah.
How you can figure any of this stuff out without being able to make these visualizations, I have no idea. I'm deeply impressed that you can figure anything out without making those visualizations. But that's
with ASCII in Vim.
yeah, right.
I have like spent a lot of time drawing those things. I like drawing a lot. Not just text drawing is also so good. I don't like any of the visualizations that you try to make like in a computer because you always want to position those nodes like in a way that makes logical sense and the computer can't do that. So that's why I always draw.
So, okay, so then these things, why are there no non-terminating ones? Well, maybe that's it. I don't know whether any of those are non-terminating, but we should probably run this. Let's just run this long enough that things are going to have terminated. Because I mean, there's some here. There were some that didn't have their final resolved form. So let's see. If we think we're going to be safe here, that's a nest graph of 5. Let's go up to 7. There. How can there be no non-terminating ones?
Try it.
Well, do you believe that that all of them terminate? I mean,
Yes, all of them. There's no non-terminating term. You can have any number there.
Is that because of the property of it being affine?
Yes, it's because it's affine.
well, I admit we're not seeing anything obviously non-terminating here.
Yeah, also the number of beta reductions that you have in this system is the same as you have if you use it on optimal evaluator. So the affine lambda calculus reduce it in any way you like is optimal already.
Well, that's because of all these paths. You're saying every path to this node is of the same. So if I pick up one of these, if I pick up this graph here, for example, right? And I look at the paths from the root node to the end, right? So let's say then what's that? Then the claim is the paths are all the same length.
Yeah.
Which looks fairly convincing to me, but we could actually check it. How do we get the sync? Isn't there a function repository function for getting the graph syncs?
I don't think there is. Still not. I haven't done it. So we have to write it ourselves or use your very unlikable general utilities thing.
No, I'm not doing that. Much as okay, so let's see. This is we have to select in here.
I usually do it with peak. You just do the peak. First you compute the degrees, right? Vertex in degrees, out degrees.
Okay, and then
We want, thread it with the equals to 0. That's what we're picking from. And that's the argument, second argument to pick of the vertex list of the same graph.
I'll have to copy the graph again.
We can turn it into a function.
Brilliant. That was vertex number 1.
I think it's always going to be 1 because it's canonical, right? And it's a root.
Okay. So now we take this graph and we say find path, that graph, comma 1, comma 24. What do we say? Comma all?
I think it's not in the list, it's just 1, comma 24. I think. Is it? Yeah. Then it's all maybe, or infinity.
No, but it finds a path from 1 to 24. Why isn't it finding that?
I'm not sure. Oh, it's the other way around.
It's upside down. Okay.
We just find all paths then.
Yeah.
There were some comments here that these drawings look like an alien language that looks like something that was found in secret parts of the pyramids.
Huh. But wait a minute. Why is there only one path there?
Try another O or infinity. Have to specify the length.
There we go.
Yeah, it looks.
Ta-da! Victor's theorem is so far is true. Okay. Okay, well, so this motivates looking at the same thing for interaction combinators. I agree. I still am very confused by what happens when you have a non-terminating computation in interaction combinators. How does that work?
So it still has the same, I mean, I'm guessing, but very confident. It still has the same shape. It just goes on forever, like vertically.
Okay, so it keeps
That's
on
all.
branching here.
Yeah, forever and
but
never
only
ends.
linearly.
Yeah, the same kind of image, just never ends.
What
But
is
it's
the
kind of
analog of this?
it's trying to go to the same point. So it's never branching like that. It's kind of branching then back, and then you see what I mean.
Yeah, right.
Yeah.
Well, can it like actually reduce, like narrow down, and then grow again, so that it's not always grows, but like that does this.
Yeah.
Like
I
Necessarily
don't
so.
think these are, well,
I
so
think.
that's a question for these. Do they ever do that? So if we look at all of these things, right, and we look at the layering, we just did that before, right? We looked at the number of things at a particular layer, right? We did that. We were able to do that for the exponential growth guy. Right. Length, the vertex out components of this, right? So then this is,
Yeah, something like that.
yeah, so we want this thing here. And so what we want is for each of these things, okay, for these, instead of what I was thinking here, we would get that list in addition to this, in addition to the, what is it? Where is that? We want, where is the actual value? Okay, well, it's of the canonical graphs. So we can strip out everything here. Yeah, we can strip out almost everything. Let's not even draw the graphs. Let's just get the parallel map, canonical graph, help.
Well, I still need to group by, or at least
Yeah, I
delete
still
duplicate.
need to do the group by. But let's just get rid of everything else. We've got the group by, we've got the parallel map, we've got the canonical. Why are we grouping by? Why aren't we just doing counts? Because at this point, we've got the graph. Okay, hold on. It's this time constrained that. There's no list there. Help me out. We're not time constrained. Well, we should probably time constrain it just for safety. 5-second time constraint. And the parallel map goes over this. Oh, I see. And then let's see if that's right. Yes, that's right. Okay. So that's the linear things. That's the 2, 3. That should be all the ones for 2, 3. Why aren't we seeing more? Well, okay, so for each of those, we can now do this thing here. I need to run off in a moment here, but for each of these, we are doing is this what's the root node here? Is it 1, do you think?
Root node.
The root node that we're starting from here, because I was trying to work out what the number of, well, maybe we should wrap up here.
Canonical graphs, I think it's doing it in reverse.
Okay, so we just want to say max of vertex list. Is that right?
Yeah, that we can do it like that too.
Okay. That's that width. And so that wants to be key mapped. No, not key mapped. Yes, key mapped over each. Help me. I mean, so we want to take, what we're looking for is the sequence that's going to go 1, 2, 1, 1 here. 1, 2, 2, 1, right?
Yeah.
Okay, so that's that thing there. And what do we want to do with this? We want to do this. And for each in the counts, in each set of counts, we're just going to do a key map.
Right.
Of this.
You can preserve the graph itself too.
I know, I want to do that.
Yeah.
Key map onto the counts. And then I want to say G, comma, that table. And we don't really want to have that 10 there. That's some kind of graph depth. Yeah, okay. So how do we deal with the table thing? That is the length of the graph from its, how do we get that? Is that the graph diameter? Let's look at one of these.
You can do graph distance because we know the maximum and minimum vertex.
Yeah, right.
Between those.
Okay, so let's go here. Kind of weird that canonical graph does it that way around, but anyway, not worry about that.
There's a question in chat here about affine, these affine graphs and directed acyclic graphs. Are they DAGs, basically? It's a
Victor, can you comment?
Yeah, I think so. I mean, it's confusing to use the word DAGs here because in the implementations we don't use DAGs, but yes, I think these graphs you can claim it forms a DAG. Not sure what happens when, I mean, unless it does not terminate, right?
Yeah, look at these sequences. These sequences are kind of what you would expect.
And we're gonna look for the bottleneck, essentially when it decreases and then increases.
Yeah, right. But all of these are uniform. They're monotonic. Not monotonic. They have only one maximum.
Yeah.
Okay, so what was the other case that we looked at? We've looked at 2, 3 here. And we want to look at 3, 2, is that correct?
Yeah.
Because I thought 2, 3, so that's all that we got in linear in this affine case. I'm a little bit surprised we're not seeing any flashing parallel maps here, but we're not. Okay. Well, all of these are one-humped creatures. What is it? They're camels, not dromedaries? Or
And you do have, can you go up for a moment? That one on the right, you do have a reduction that skips a level, like
Yeah.
that.
Why does
That
it want to
point.
say 1, 3, 2? Why doesn't it come back to 1 at the end?
Because the levels are now not very well defined. Because it skips.
Oh.
Yeah. So that one
Oh,
on the
and so
left
then the
is
total of those numbers isn't the number of nodes in the graph. Is that what you're saying?
Yeah.
yeah, you can just count. It's not the same.
Yeah, 1, 3, 2. Let's look at that one. Okay, so there's a foliation question here. Okay, nominally, it may be that by construction, we always are doing these things that are sort of one-humped things. Let's just take a look. Okay, but we've got this graph here, and you say that could be 1, 3. Oh, I see. And that's kind of 4. Huh. Yeah, well, it matters how, okay, so maybe that's, does that surprise you, Victor, that that happens? Because that's a little bit
Yes.
different from your, I mean, that's your grid thing, but it's a grid that's been knitted together, not as a, you know, as a kind of cellular type grid.
Yeah.
Can we do extract the actual lambda term? Minimal.
Yeah,
That's
I would love that.
linear one that does the skipping.
Okay, all right, okay, fine. Where is that?
Before you do, let me ask you a quick question. Is there any other system, like model of computation that you have observed that has this same kind of appearance? Is that how you say in English? That same look? Because I guess all of them look like the lambda calculus, right? With all those crazy.
I think so. I think so. Yeah, I think so. I mean, again, but I think the reason, as you've identified, the reason is that lambda calculus is doing more per step than you're prepared to do, right? So I mean, I'm thinking about multi-way Turing. I think multi-way Turing machines look like this as well, for sort of the same reasons.
Yeah, they I see Turing machines as one-dimensional interaction combinators, so that makes a lot of sense to me. But
Let's find that lambda term that where was
ju
it?
ju just, do the sky combinators look just like the lambda calculus?
I think
It's
so.
kind of,
I
yeah,
think
okay,
mostly, yeah.
interesting.
The all right, let me just pull out. Where is it? That is, oh God, how do we, you know what? It may be simpler to just be really stupid about this and just go, I think we should do something really, really stupid here. We should take that thing there, and this is now 3, 2. Nope. Okay, so it's this expression here, 87. I'm going to do something incredibly hacky. Ag! So much for that idea.
Okay, try position all, because position is level 1 by default.
Oh, yeah, right.
Nah. It also may not look at the keys because it's inside of association.
Okay, hold on. We can look. Let's do all.
I think I know what's happening.
Drat. Just a minute. We got to be able to find this guy.
Yeah.
Okay.
Try normal of just to keep trying for try normal of percentage 7 because it doesn't look inside of the keys. Nah, it's just maybe it's not
I think
exactly.
it just had a different canonical form. All
Maybe
right, let's take a look here.
can we just find?
Sorry, go ahead.
Yeah, I think we can
Well,
just find.
Look, there's one.
Yeah.
Look,
No,
there's
look, there's even below. Yeah, we can take this one. I think they're
Which one would
simple.
you like? This one here or this one here? They both
That looks
they both
similar.
have that property.
Yeah. I think that one.
Here, let's just look up the simplest one that has that property.
That's a better idea.
That one.
Yeah, but look, there one's even up here.
Yeah.
But I do think I know what's going on.
Okay, here's
Please
one.
tell us.
No, that is a simpler one.
On the left,
That
just on the left of that.
yeah,
This one.
that's better, much better.
Yes, right. Okay. So what's happening here?
Do you want me to?
Well, I guess. I mean, yeah. Let's maybe we can draw this thing with all its.
So
terms.
I have a theory, okay? If you want to, I can try to.
Actually, you know
okay,
what? I'm just going to
go
make a
ahead.
picture first, and then we can have a theory.
Okay.
Also, Victor, if you see in the chat on the YouTube channel, there's some comments there from T6 that might be helpful.
Sorry?
T6 was commenting in the chat.
Oh, that's what I was going to say. Yeah. Okay, so when you want, I can explain what's happening.
Okay. Go ahead.
Oh, okay. So the thing is, in the affine lambda calculus, that's a difference from the affine lambda calculus compared to interaction combinators. So on interaction combinators, that will never happen. On the affine lambda calculus, when you drop a lambda term, so if you have a lambda term that does not use its variable and it's applied to some big term, that dropping, that erasing or like garbage collecting of this big lambda term that has been dropped, it happens in a single step, and it should not. It should take some steps to collect that memory. So that's why we have like those shortcuts where some reductions do not show up in this graph. And like as T6 pointed, my theory, and it's probably right because T6 just said it, but if you do filter for linear lambda terms instead of affine lambda terms, then
Yeah,
that will
that's
never
what I
happen.
was going to guess
Yeah.
as well. But this won't show up. All right, let's just try that one last thing, and then we should wrap for today. And then I think we could. It would be fun to continue, and maybe next time we could look at interaction combinators instead of lambdas. And that way. All right. So here we are doing, instead of max less than or equal to 1, we're just doing max equals 1, right? Yes. And yeah, we're going to get some fairly big things here, but we're going to get fewer. Okay, let's take a look. Oh, what's that guy doing? That's
So
that
if
same
you do the
deal.
max, you still allowing for zeros if you do max equals 1.
Oh yeah, stupid. Yeah, sorry. Sorry.
You should do mean. and max.
I don't
Should
want to
like,
do min and max. I want to do min max
yeah, min max.
equals 1, 1, right?
Yeah, yes.
Otherwise known as a union equals 1. Da-da-da-da. Well, looking good. What's happening with that guy? I think that's just a 3D version, I think. Let's see. Help. Just do this. Why are these doing that? Why are they flat like that?
Can you spring electrical it?
Yeah.
Because it
Are they
fixes
doing what?
the-
What's that?
you may be able like, oh yeah, okay.
Yeah, well, that's okay. There's nothing too wild. I mean, that thing should be like a true tree rooted like that, right?
Mm.
Okay. That's fine. So let me just. And obviously we can test this. Well, that probably hasn't come to equilibrium, although these are still, so those ones at the end are, I mean, you claim that with this linear lambda terms thing, that you'll never get unbounded. Well, you say you might get unbounded growth, but it will be sort of grid-like. I really want to just run this one more time.
So, in this version, what you're using, like affine lambda calculus, you never have non-terminating terms. On interaction combinators, you could like have those terms that don't end, but you get the same kind of picture. But one thing that you could do, if you allow for recursion on this language, then you can have non-termination and you still have this property. And that's actually very interesting because you can get a strongly confluent language just like interaction combinators, but without needing graphs and nothing like that, just on the lambda calculus, if you just add recursion. So like
What
top
do you mean by
level.
recursion?
I mean that you can have top-level recursive definitions. So, for example, you can define some term, give it a name, and then that term can refer to itself. So that language that you're using right now is not Turing complete. But if you do add recursion, it will be Turing complete, and it will still have this property without needing to use interaction combinator. So that's actually a very interesting language to consider. Like if you are implementing like some kind of programming language and you want strong confluence and you don't want to implement interaction nets for some reason, yes, just go with the affine lambda calculus, add recursion, and you have that, a Turing complete
Well,
language.
we could try. So an interesting thing would be to try this enumeration. Okay, so what happens if one includes a recursion operation?
Mm.
All right. Well, now you've given Victor, you've given a pretty good set of motivating examples for looking at interaction combinators. So that's what I want to do next. Is let's see the same thing for interaction combinators. Let's see what what the simplest interaction combinator programs actually do. Yeah, it's great. All right, I got to go to a completely different thing here. Actually, the thing that I'm about to look at is some things to do with biological evolution. And actually, some of those kinds of evolutionary processes one can imagine applying to these lambda expressions and to interaction combinators as well. But I think that's for another time.
Can we publish this to a cloud link or something? We can
Yep.
share it with the
Yep.
audience.
It may be somewhat big. I don't know how big it is. Let's just do that. doesn't seem to look big.
Is it on Dropbox? If it's on Dropbox, I can.
No, I'm just doing it.
Can
So
pick it up.
it's in our working files thing. All right, let's do this. Let's publish it to, I'm going to send it in chat here. And then I'm also going to use our cool feature of being able to show the QR code. Is that really, hold on, except the QR code went on the wrong screen here. There we go. So
Cool.
for anybody, just point it at the screen or something, although I'm sure we have ways to send it through chat. And that should be the Cloud Notebook version of this. And for anybody who's interested in playing with this, if you just you can just sign in, you can start playing.
So cool.
Yeah, I think all the Nick's packlets are all on public packlet servers, right? So you just do the same packlet install stuff. And the only thing that might be different, where your mileage might vary, is that I happen to be running this on 200 cores. So some of the things that we were doing will probably not be as zippy on just one machine.
I think diagrams wouldn't work. Well, I can actually reduce the version there too. If you not use
Oh,
40.
that's right. They're depending on an unreleased version right now. Right, but
Yeah.
you could probably, they probably don't actually depend on it, do they?
No,
But
it's
most
just-
of what
it's
we
just-
did here didn't use that, right?
I can reduce the version right now. It's not a problem.
Okay.
Just to publish to the same link, and it should
Yeah.
work.
Fair enough. Well, that was fun. Thank you all very much. And until the next time.
That was very, very fun. Thank you so much. See you.
Thanks for joining us. All right.